Uh, so it is crucial that I get across to you the big idea of calculus. This is basically half the calculus you're about to learn. And it's equally crucial that you don't think it's some kind of trivial, simple thing like, oh, if g of x is x squared, then the derivative is, does anybody know that derivative? 2x. Now, if that, oops, I didn't give you notation. If that's all a derivative is to you, then you're wasting your time because that's meaningless. That's just babble. Who cares? It means nothing. Yes, there's a great shortcut that you will not be using for quite a while for certain problems only. But to actually understand what the heck it is, that's today's lesson. Right? Yeah, there will be some shortcuts later on, but the true idea is today. All right, so here we go. I have lots of goals today. We'll see. I have used calculator to estimate the derivative. I thought through or kind of timed how long this is going to take, and that's not happening. So watch that. We'll get to that tomorrow. Okay. So the goal of a derivative is to find the rate at which a function is changing at a tiny instant in time. Now, graphically, that would mean a tangent line. Say, I think on your paper, I have A labeled here, yeah? Okay. Say we wanted to draw a tangent line at x equal a. Now, that's actually technically one point. And rules of geometry say how many lines are possible through one point? Infinitely many, actually. I can't draw a line through one point. I can draw infinitely many lines through one point, right? It really takes two to tango. It takes 2 points to make a line. But we'll get to that in a second. Right now, would you try and rough in a tangent line? Take a stab at where it would be. I would say it would look something like that. Do you agree that barely touches? Oui? Oui. Okay. Now, I want to find how fast is that changing. When I say how fast is it changing, I mean how fast is y changing with respect to changes in x. As x changes 1 unit over, how much would y change? That's a rate of change or a ratio of change, yeah? Notice the ratio of change. If I were to draw, oops, didn't mean for that to happen. If I were to draw a change in y and a change in x, look at that little triangle. What's opposite to adjacent? Oh yeah, it's tangent. The ratio opposite to adjacent is tangent. Okay, so moving up. Oh, that's not supposed to be there. Wow, that was really bad. What's going on here? I don't like those. That's boring. Delete. My bad. Sorry. Boom, boom, boom. Okay, sorry. Now, the idea of a derivative is not to start right at the tangent line, it's to start with the secant line. Remember, a secant line is a line drawn through 2 points, all right? So would you take point A, and I want you to find a point that's 5 units to the right of A. That's a good sign for my lesson. Okay, that point right there and that point right there. I could draw a secant line through those 2 points. A secant line is a line through 2 points. I'm going to draw a line through those 2 points. It would look something like that, yeah? Right now, that's probably not very close to my actual tangent. So to get closer to my tangent line, instead of going 5 units over, I'm going to go 4 units over. So would you below go A, that point A, and find a point 4 units over. 1, 2, 3, 4. And draw a secant line there. And then find a point A and a 0.3 units over there. And draw a secant line there. You see the idea, I think. And draw a secant line there. Oh, goodness. And 1 unit away. Oh, shucks. A and 1 unit over. Okay, so you might say then the idea is that as the points get closer and closer together, you can see then that the secant line is getting closer and closer to the tangent. Now, if you were to show all those guys together, something like this, here's the tangent line I want to find, yeah? I don't like that. Okay? The secant lines went something like this, then this, then that, then that. As time goes on, the secant line approaches the tangent line. So we're getting a better and better, closer and closer to the tangent line. Again, this is necessary because I can't really draw a tangent line through 1 point. I have to take 2. But I have control over where the points are. I get really close to the tangent line if the points are really small and close together. Okay? So that's the idea. Now, how do I move something in terms of stuff we just learned? How do I say what happens as something approaches this? That's saying a limit. Yeah, a limit. So it's all about the limit. Now, the graphical is great, and I'm visual, so it helps me understand, but really the analytical is what we're going to find derivatives on. We're not going to count boxes and try and estimate the tangent line by counting boxes of the slope. It's not very exact at all. So we need a more I overlapped that, sorry. Already did this. We need an analytical way to go about it. Now, in essence, then, the derivative consists of 2 parts. This is important to me that you understand what the definition of the derivative does, where it comes from. Okay, not it's this delta x or this h graph. I don't know. You do this stuff. Okay, I am going to ask you a question on a test. Why is the limit there? In the definition, yeah, here's the definition. I'll give you the definition. Why is the limit there? Why is this there? All right, so it's important that you understand the 2 ideas of the derivative. We started by finding a secant slope. Okay, now say we were always talking about the points A and F at A and some other point. Now the other point was kind of all over the place. We took sorry, for the other point, we took one that was 4 away, and 3 away, and 2 away, and 1 away. So this other point was always some changing amount away. Do you agree? Okay, so as far as the slope, what happened? The points, there were A, F at A, and some point away from A. Now, there are 2 ways to call that. We could say that it's really, how much do you call that distance away? You know, that 4 away, 3 away, 2 away. Some books call it h. Some books call it delta x because you're changing x by so much. I like to use h just because of the simple fact that it's going to be a lot less writing over the course of hundreds of these problems. All right? For that x, then, you would have the y that comes out when you put that in. X is just the F result when you put that x in. Yeah? Now, when I went to find, if I were to analytically find the slope between the 2 points, which, by the way, is the same as the average rate of change, or the secant slope. How do I find slope between 2 points? Algebra 1. Change in over, thank you. So let's say change in y. Change in y over change in x. Change in y is f of a plus h minus f at a over change in x. What's change in x? Yeah, it's a plus h minus a, so that just amounts to h. Now that's the slope between any 2 points. A and a point 4 away, A and a point 3 away, A and a point 2 away. We don't really want the slope between 2 points. We want to then bring the points closer together. Now, if h is the gap between the points, then we get them close together, close, by doing what? How would I get the points closer together? Take what? Yeah, making h smaller by taking h down to 0. And we do that by a limit. So now we're going to take the slope calculation between 2 points, and we get the points closer together and see what happens by saying what happens as h goes to nothing. Well, that means those points are getting closer together. That picture then is getting closer and closer to the tangent line, and we start to approach our slope at the point of interest. This then is the definition of the derivative at x equal a. The notation for that, there are actually many, but we'll start here. F prime at a. This means, this is read as f prime of a, or at a, or the derivative of f at a, okay, is equal to that their calculation. The slope between 2 points, and what happens is the points get closer together. There are 2 components to derivative, an expression for the slope between 2 points, and then the idea of getting the points closer and closer together. Would you also just get a wee bit of vocabulary? This is often called a difference quotient. The derivative then is the limit of the difference quotient. Think about difference quotient, analyze it, that makes a lot of sense. Difference because it's change in y over change in x, and quotient because it's fraction or ratio of those two. You follow? Okay, cool. All right, so if we were to use the definition of the derivative to find f prime of 2, given that f is x squared plus 1, it would be tempting, especially for you calculus students coming in, to say, oh, that's 2x. But does that answer the question? No, you did not use the definition of the derivative. So you would get a big fat 0, nothing, okay? It does not ask you for, I just don't want the derivative, okay? I want you to use the definition of the derivative. So f prime at 2 is, first of all, let's get the slope then the limit, right? So the slope is between 2 and a point h away from 2. Okay, this is, if you like, you could do this, but it's not going to be necessary after a few of these. All right, now if I go h away from 2, that would be 2 plus whatever that amount is, and then f at whatever I get when I put that x in. So those are my 2 points. Set up the slope calculation for me, please. Technically, you could use either order, but typically we use the 2 plus h first. So, change in y, please. Change in y is change in f. Speak. F of 2 plus h minus f of 2. That's the change in the y between the 2 points. Over change in x. H, okay? Now, what does that represent right now? Is that the derivative? It is not the derivative. That's the average rate of change. The difference quotient. Beautiful. It's the secant slope. It is not the slope at a point. It's the slope through 2 points. To make it the slope at 1 point, we then take the gap h down to 0. All right. Now that's the setup. All right. At this point, we now use the function that's given for this problem. That general definition of the derivative would be true for any function I gave you, but now I get into which this problem is, right? Now, I haven't done the limit yet. That's still waiting to be done. I need to find the average rate of change kind of expression first. What is f of 2 plus h? How would you do f of 2 plus h? Doesn't that mean put 2 plus h into the function, yeah, for x? So that would be 2 plus h squared plus 1. Wouldn't you agree that's f of x plus h? Putting x plus h into the function in x's place. Minus f of 2. That means putting 2 into the function in place of x. So that would be 2 squared plus 1, or 5, right? You see what I mean? Here's the function. If you put 2 into the function, you get 2 squared plus 1. And all over h. Wait. Let's clean it up. The limit as h goes to 0 of, what's 2 plus h squared? 4 plus 4h plus h squared plus 1 minus 5. Over h. Sorry, I did not give you a lot of room here, but we'll work it out. Simplify the numerator, please. What do you get? H squared plus 4h, and the constants all drop out. 5 and 5 go away, yeah. Over h. Simplify that, please. Do you agree that I can't do that limit right now because it's 0 over 0? So we're going to do some algebra cleanup here. Okay, so what can you do? H plus 4, sorry, h plus 4. And so as h goes to 0, what is h plus 4 approach? 4. Now, it would be peachy if you understand, after doing all that, what the heck you just did. You pushed a bunch of symbols around. Do you know what it means? No? Okay. Probably I didn't either when I was initially. Hey, graph. What does the graph look like in this problem? So parabola shifted up 1. Okay, so it looks like this, yeah? When you find a derivative, what are you finding? Graph tangent slope. At what point here? At 2. So you're saying if you were to graph a tangent slope at 2, the slope would be 4. And it is. Perfectly 4. Okay? That's what you found. You found the slope to the curve, or the tangent slope to the curve at x equal 2. Now, that obviously represents the slope of the curve at 2, as I just said. If I then asked you, okay, now find the slope of the curve at 3, and then find the slope of the curve at 4, and then find the slope of the curve at -8, that would mean you would have to redo this over and over every time for each new number. Are you with me? And that would be a drag. So it's then nice to say, all right, forget that specific number 2. I don't want to redo this over and over again. I want to find a rule that will do this for any point, and I can just go straight to plugging that number in. So save me some time from having to do this over and over again. So rather than actually finding the derivative at 2, we more often find the derivative at any point and then use it later. That's the goal now. Instead of finding at a specific value, we're going to find it at any point x. So the derivative at any point x. For the same function above, using x squared plus 1, let's find a derivative for all x. And then, once we have that, then we'll use it for those three separate slope rules, okay? So, again, the derivative is just two ideas. The slope through 2 points, and then the limit makes them go to 1, or approach 1. So let's start with the points. What are the points? Now, before it was 2, f at 2, but I'm trying to get away from that specific points, and I want to go to a general point. So this time I'm going to use x, and f at whatever that x is. Okay. Now I still need to find a point a little away. That little away, I've been using h, but you could use delta x if you like. But if I go h away from x, that would put me at x plus h, or x plus h, yeah? And the y value for that would be f of x plus h. So now, using the two parts of the derivative, slope between 2 points, what's the slope between 2 points? Those 2 points. Slope is changing y over changing x. F of x plus h minus f of x over h, yeah? Now that's the slope between 2 points, or the secant slope, or the average rate of change. Now I'm going to take the points closer together. How do I do that? Take the limit as h goes to 0. The gap between the 2 points goes to nothing. The points get closer together. In terms of what I'm going to be finding, when I'm done, this will be the derivative. And so I'm going to use this notation, f prime, at what point? We're looking at 2. No, it'll be at any x. Okay. All right. So now that I have my basic idea down, I go to problem specific. In this case, the function is x squared plus 1. So f of x plus h, if I put x plus h into x squared plus 1, then it would be x plus h squared plus 1. Subtract, in parentheses, f of x. What's f of x? That's that. Now I need this. F of x is just x squared plus 1. Make sure you use parentheses, okay? Otherwise, you're not going to distribute that negative, and you're going to get the wrong derivative. All over h. All right. Now, every time you do a derivative, you're going to have a 0 over 0. That's by virtue of you're getting the points so close together that change in y is 0, change in x is 0. So that's not going to be direct substitution possible. Every derivative, every one starts at 0 over 0, and so you'll always have to do some algebra cleanup to make the limit happen. So, if I do a little cleanup, x plus h squared is x squared plus minus, I might as well distribute the negative. I don't know why I put those brackets there anymore. Isn't it x squared minus 1 once that negative is distributed? When I combine my terms up top again, I shouldn't have put those brackets there. But what happens to the x squared? Divides away or subtracts away. 2xh stays. H squared stays. What happens to the 1? Goes away. At that point, I still have 0 over 0, but then I can divide out an h. If I divide out an h, what do I get? 2x plus h. And if I then evaluate the limit, as h goes to 0, this would be like 2x plus 0.1 and 2x plus 0.001 and 2x plus 0.0001. It would start to approach just 2x. Now, you can see that's a little different outcome. Here, I actually got a number. The slope is 4. It makes sense that this derivative is actually dependent on x because the slope will depend on where you find the slope, right? So it's a rule for x, makes sense. Now, I could actually answer the other questions pretty doggone easy. F prime at 3, what is it? 6. It's just 2 times whatever the x is. 2 times 3 is 6. The slope at 3 is 6. What about f prime at 4? 8. What about f prime at negative 8? Negative 16. Now those are nothing. Pretty easy. Okay. Think about, I'll get to the definition in a second, but think about the graph. We said x squared plus 1 looks like this. Tell me about every slope on this side of the vertex. All those slopes are? Why would that have to happen? If the derivative is 2x, then if you put in a negative x, you'll get a negative slope. That makes sense. What about at 0? What's the slope? It's flat. It's 0. At x equals 0, the derivative is 0. That makes sense. At positive x's, those slopes are positive, and that would be positive. So all that makes sense. Wouldn't you also say that as x gets bigger, the slope will get bigger? That makes sense too. Bigger, 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 really big, really big. And so all of this is super logical. You follow? And this is where Leibniz and Newton said, oh, dude, this is killing. This is amazing. I just invented calculus. All right? So here's the definition of the derivative. F prime at any x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. Tell me, what does that do, that difference quotient? What is it there for? Why is it there? I fail as a teacher. I am sorry. Why is it there? It finds the slope between 2 points. Why is the limit there? To make the 2 points get closer together. Okay, slope between 2 points, get the points closer together. That is the idea of the derivative on all 3 definitions of the derivative. We'll talk about it tomorrow. But that's always the idea. The notation's all different, crazy, but if you remember those 2 ideas, slope between 2 points, get the points close together, that's a derivative. That gives you change at a point, which before this point, 500 years ago, was impossible. 400 years ago, excuse me. All right. Would you try that one, number 1, please? This is going to start to build on some of those skills you have been doing in limits lately. You'll see. I'm going to follow behind you. Make sure you're on the right track. Oops, shucks. Now is this the at specifically at a point or general x? At a specific point. So instead of the points would actually be 2, f at 2, and a point a little away, 2 plus h, f at 2 plus h. All right, so it's more like the first case we did, where you have an actual number in there. Okay. All right. So if you did, now you might have a question for me. What if you did f of x plus h? What if you have x's in there instead of 2? Are you doing it wrong? Yeah, actually, it's not what I intended, because in order to get multiple choice practice, I would like you to do it this way. But you're not doing it wrong. The only thing is, at the end of the time, if you have x plus h and all that stuff, you're going to have a rule for all x's. And to find f prime of 2, you will then, at the end, have to plug in 2 and see what you get. Okay? Now that's okay, but I didn't specify, probably should have, but there are a lot of AP problems where you're asked to recognize what's going on, and I really want you to get some practice showing it like this, so that you know, oh, that's the derivative specifically too. Okay, so if you already did it the x way, that's fine, but if not, continue on with this. Get problem specific. it, that goes to 0 over 0, right? So like all derivatives do. What can you do algebraically here to make this happen? Rationalize the numerator. What do you multiply by? The conjugate, 2 plus h plus root 2 over itself. If you do that, it becomes the limit as h goes to 0 of, what does the numerator become? 2 plus h minus 2 all over h root 2 plus h plus root 2, yeah? Simplifying that, 2 minus 2 goes away, you're left with an h. What happens to the h? Cancels out, and you're left at the end with 1 over 2 plus h plus root 2. Now let's, before I run it in for the touchdown, let's pause here. This is always a learning Calc 1 student issue, error, / makes my teacher crazy. Look at your work. Do you have the limit here and here and here? If you don't, then would you please hit yourself like that and never do that again? You will write the limit every step until you actually put in 0. It's there. And it's not, oh, write it in later. No. If you don't write it in from there to there, not true, -1. From there to there, then it's back. -1 again, not true. Okay? Every time you say something that's not true, -1. Okay? The limit is there until you actually get the limit evaluated. Now you can put in 0. If you put in 0, you get 1 over 2 plus 0 rooted plus root 2. That then is 1 over 2 root 2. If that was the form of your multiple choice, you'd be good. It's possible, though, that they rationalize the numerator if it's a multiple choice. On your homework, by the way, I'm fine if you leave a root in the denominator. I'm okay with that. We have bigger fish to fry. But if the multiple choice was one and such that it didn't have that choice, you might look for one with rationalized, which is root 2 over 2 times 2, or root 2 over 4. Yeah? Are you with me? That's f prime at 2. Slope of the curve at 2. Derivative at 2. Okay. Try the other one, please. This one won't take too long. You'll see it goes pretty simple. Again, people who have seen this before, or maybe can see this coming, you might see this is going to be pretty straightforward. But get into the problem and use the definition because it says to. In this case, the points you're using are x and x plus h because they want the derivative at a general x. How's it going? I'll slow down. Sorry, I've done thousands of these and just learned. See you turn the right track. So if you're done, make sense of your answer. Ask yourself, why is that? Does that make sense? Why does that make sense? a lot of stuff drops out, yeah? And in fact, you only get the limit of 2. This sometimes kooks students out. Okay? H is 52. What's 2? 2. H is 51. What's 2? 2. I don't care what H does. 2 is 2. H can go to 0, sure, whatever, but 2 is always going to be 2. Now wait a second. I thought when I did the derivative as a rule of x, I was supposed to get a rule that depends on the x you put in. How come this derivative doesn't have an x? Because it's a line. Talk more. The line, would the rate of change depend on what x you asked about? No, the rate of change would always be 2. Okay? The derivative of a line is always equal to the slope. The slope is the rate of change. Okay, good deal. How'd that go? Real quick question. One more thing. Derivatives or calculus, all calculus is notation crazy. There's so many notations in calculus, you're going to love it. It makes you feel smart once you understand what the heck all these symbols mean. Now, if I were to look at the slope here, the secant line, this actually is true change in y, delta y, and true change in x, delta x. You follow? At the tangent line, however, let's say it's right in here. Here's the tangent line. Now we said it's a fundamental truth of math. You can't draw a single line through one point. So although it doesn't look like it, there is a microscopic triangle here. There is a tiny little triangle. If you zoomed in, there's the smallest possible triangle here. It's, in fact, like Leibniz called it the infinitesimal triangle, for which he got mocked for 10 years after he invented the calculus. Infinitesimal, what does that mean? It's something that's 0 but not 0? That doesn't mean anything to anybody, but it's actually makes a lot of sense. Now, because it's not a true thing, a delta y and a delta x, it's more of a theoretical exercise, he called it actually a differential in y. And instead of calling it delta y, he called this more theoretical dy, standing for a tiny differential in y over dx. This little change in y in that little baby, smallest possible triangle that's not 0 is dy change in y and dx change in x. This is another notation for the derivative. This also means the derivative in Leibniz notation. Okay, Newton actually used what's called a fluxion, a little dot instead of a prime, but whoever or she, whatever, his notation got changed a little bit a couple of years later, and so that's what the prime notation is kind of from Newton. This then, notations for the derivative. We know, actually, so this means the derivative of f at what point? At x equals 3. That read as, how do you read that? F prime of x, or just f prime. Often if you asked a BC kid, he'd just call that f prime. Sorry. But it's f prime is the derivative. Now this is the derivative at any x, yeah? Same notation. These mean the exact same things. This is Leibniz notation, but it is also the derivative. Now, for the sake of preparing you for related rates and such, you would often, if long form, again, most people just say that's the derivative. But if you were to read this in the proper way, it's the derivative of y with respect to x. Now, when you do multivariable, that'll make more sense. But a variable could depend on a couple things. So I could look at how your grade in the class changes with respect to your homework grade. That would be more like D total, D homework. Or I could say, how does your total grade change with respect to your test grade, which would be more like D total, D test. So you have to say with respect to changes in this or that. We'll talk about this more later, but derivative of y with respect to x. If this is at any x. If you want to specifically use this kind of idea, I want the derivative at this number. In Leibniz form, then you would actually have this bar here and say, give me the derivative at x equals 0. That's what that means. It would be like f prime at 0 in function. Okay? Well, that is that. I'm exhausted. How'd the homework go yesterday? Rough. Okay. Let me give you. Oh, shit. This, by the way, is in the book. You are in the book now, so you'll get to take your book home. I typically, it might not seem like it, but I try to be aware of your time. And so I go through every problem and say, is it worth their time or not? If it's not worth their time, sometimes I just dump that problem. Sometimes I replace it with something you need more practice on. So you might see some either skipped or replaced. So don't just mindlessly crank out 25 problems. That's just there. Okay. The homework from last night. If we get through all the questions, great. If we don't get through them, then we'll probably just turn it in tomorrow. By the way, I have 2 homeworks and back. Man, those summer reviews killed me. Taking about 5 hours to grade. Is this the question? Yes. Oxford. Here's 2 homeworks, summer review and limit homework. All right. Again, if we don't get through all this, then we'll finish going over it tomorrow. I'm aware you don't have 7 hours. So, for 1, the idea, did I post the key to this? I didn't post the key to this, did I? Okay, so it's all new. I guess we are going to have to do this. To use the IVT, remember the idea is that you start by saying, is the function continuous? Is it going to go from one point to the other in a continuous way? In this, number 1, is h continuous?
Yes.
Yes, you need to say it. Okay? Then you say, what happens at the endpoint? Where does it go from and to? So you need to say h at 0. This, by the way, should have been at x and x, not r. R's something else. H of 0, what'd you get for h of 0? Negative 5, right? And what is h at the other endpoint, 5? When you go to 5, what does h start to take on? 11. The y values went from negative 5 to 11. Along the way, do they have to pass through 3.3? Yes, say that. 3.3 is between negative 5 and 11. So now the conclusion. By the intermediate value theorem, there must be an R between, okay, one of the issues with this, and it's kind of confusing, is R an x value or a y value? An x value. So is R between 0 and 5 or negative 5 and 11? 0 and 5. Really, all you have to do is kind of regurgitate the question and say yes, blah, 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 blah. So there is an R between 0 and 5, and you can use inequalities, you don't have to say it in words, such that h at R is 3.3. I proved that by saying it goes continuously from one endpoint to the other, and the point they ask about is between the two they give me, so yeah, it has to pass through 3.3 along the way. Do I need to draw a little sketch of this, or do you get the idea?
Yes.
Okay, cool. Here's where all heck started to break loose. This was disastrous. Both of these examples are stinking lame problems. 2 is not what I intended. Did anybody get 2? What's the first thing you do with 2? Yeah. Okay, so if you know your stuff, this problem should actually take you about 5 seconds. Is H continuous? Or is K continuous? I don't know. It doesn't say. So, you're done. Not necessarily. Boom, it's done. I don't know. It goes from there to there. So, don't just rubber. I didn't actually intend this. It's not like I have some grand plan. I'll make sure they check continuity. I just forgot to put it in there. But, with the problem the way it says, it does not say K is not necessarily continuous. So whatever it does from one point to the other, I don't know what it does in between. So all I can say is that K is not necessarily continuous, so not necessarily K equal to 0. Not necessarily. K could equal 0, but it doesn't have to be. It's not a must be. Now, for the sake of argument and the sake of practice, if you have that one, you don't have to redo it. But for the sake of practice, let's go with what my intention was, and that is, let's pretend if K was continuous, which was, again, my intention that you get practice. All right, so you would then say, all right, K is continuous, and that's given, or should have been given. What would you then get into in this 3-step process? Yeah, you find the endpoint. So you go at K at, the endpoints are, you want to find K at 3 and K at, oh, that's the answer already? K at 5, right? K at 3. What is K at 3? Well, let's go slowly. Do you agree K of 3 means put it into F and then add it into G? So that's G of F of 3. What's F of 3? 3. That goes into G. That then is 4. Okay? K at 5 is G of F of 5. We're not going to get through all this. You can keep this stuff tomorrow. I'll put my key online tonight. You can look it over, and we'll go over some more questions tomorrow. I would rather have this done well than done quick, so we'll finish going over it. Okay? Start tomorrow. This is right? You're about to leave.
Yeah.
Oh, that should be 40, sorry. It's not a 40. And then also make it double one from yesterday. Yes. Get it to you. It's right there. Actually, let me stop this.
No idea.